Hi, so this is some start time feedback for A2 Evaluative Task 1, determining the order of a reaction from May 2011. A few things to note. First of all, there's a plethora of information given to you at the start of the coursework, so you have to keep referring back to this during your piece. You can see that there are two equations, equation 1 and the second equation, which is instantaneous, that immediately follows equation 1 once you've had your hydroxide ions produced. The other thing to recognise are the two solutions that are prepared and the things that they contain. And finally, you need to be aware of all of the information that's presented to you. That includes the data from experiments with volumes and T and 1 over T, and also the quantities that are added together. So if we begin for question 1A, the volumes of A are measured with a pipette with an error of 0.06, and the volumes of B and water are measured using a measuring cylinder with a maximum error of 0.1. When we're asked to give the experiment number in which there is a measured volume with the greatest percentage error, the first thing that we have to look at is which of those two volumes has the greatest error. And obviously that's 1. 1 is bigger than 0.06. This tells us that it's either the volume of B or the volume of water that is going to be the substance which will introduce the greatest error. When we look at the table, volume of B and volume of water, what we're actually looking for is the smallest volume, which is 10. So you can see that the volume of B that is measured in experiment number 6 is 10 centimetres cubed. And reflecting back to our work on errors, when we're calculating an error, we look at what the error is, divided by the quantity that we've measured and multiply it by 100. So in this case, if we're measuring a volume of 10, our percentage error is going to be 10%. Whereas when we are looking at 1 over 80, our percentage error would be 1.25%. So 1 over 80 would be the error for the volume of water. Similarly, you could think about 1 over 20 gives us a percentage error of 5%. 1 over 70 multiplied by 100 gives us a percentage error of 1.42%. So the thing that we're basically looking for is the smallest volume of either B or water, and that is because of our 1 centimetre cubed being our greatest error that we're measuring. The next thing it's asking us is to calculate the percentage error for the measurement of time. If we look, we can see that time has got a maximum error of 0.1 seconds. So again, we use what is our error, 0.1, divided by the measured, divided by the measurement, 14.5, and multiply by 100 to get our percentage error. Now 14.5 simply comes from the table. You can see there experiment number 1 takes 14.5 seconds, and we know that that's the number we're using because it states here in experiment number 1. If we move on to the next questions, in experiment 1, the phenolphthalein changes colour to pink after 14.5 seconds. Explain why there is no colour change before this. We have to remember from our equation that we have hydroxide ions that are being released in equation 1 there, and then in equation 2 these hydroxide ions are being used up. So as the hydroxide ions are used, they are immediately being used up. So up until 14.5 seconds, when the reaction ceases or when the reaction changes colour, the OH minus that is produced is removed by those HSO3 minus ions. In experiment 3, describe what happens to the SO3 2- concentration in the first 21.7 seconds and then in the second, or after 21.7 seconds. And it's specifically 21.7 seconds because that is the time t that was measured. Now the reasons for this, in the first part, we know the SO3 2- is removed, but it's also being made. This means that overall the concentration will remain the same. So if we look here, we can see that the SO3 2- is being removed, but then it's being reformed. So as long as everything that is removed is reformed, then we know that we have got a constant. It does fall after 21.7 seconds, and the reason that it falls is as follows. Once all of the HSO3 has been used up, so if we look here, we've added a small quantity of HSO3 minus, and it tells us that in the exam paper. Once all of that has been used up, then we are in a situation where we can't have it reacting to reform SO3 2-. So as soon as this is gone, this can no longer be reformed. This will still be being used up in equation 1, but we're not reforming any of the SO3 2-. So constant to begin with, and then in the second part it will fall because it is no longer being reformed. For D, plotting an anomaly gets you 1 mark. Line, which is straight with a ruler, and a line of best fit through 0, 0 will get you the next marks. So my graph that I've drawn, the red line, as you can see, we've got 1, 2, 3, 4, 5, 6 points. They are all exactly plotted correctly. We've then drawn the line of best fit, which goes through the origin, because at volume 0 the rate will be 0. It's going through as many points as possible, and we've circled the anomaly that we have got there at 25 seconds to suggest that there was an issue with that particular experiment. The line of best fit must go through 0, 0, or you cannot have the marks for this section. The next part of the question is asking us to use the graph, that gives you a clue, to estimate what time would be measured using 10 centimetres of A, 30 centimetres of B and 60 of water. Now the important thing here is the 30 centimetres of B. Because it's B that is on our x-axis, we take a line up from 30, so for B, we read across to find out what 1 over t is, and once we know what 1 over t is, we can then process that data. So if we take my example, yours might be slightly different depending on your line. My reading at 30 is 0.038. This tells me the value for 1 over t. If I need to convert 1 over t into t, what I'm basically doing is 1 over 1 over t. So 1 divided by my reading from the graph, 0.038, and this gives me a value of 26.3 seconds. In the mark scheme, it tells me to accept any number between 25 and 27 as long as it's been processed from your data. The next question is reasonably straightforward. You could do this in GCSE. We are sketching a line to show how we would expect the rate to vary with a volume of B at higher temperature. Higher temperature means more kinetic energy, more particles that have got above the activation energy, so we end up with a faster reaction. You can see that my line here is indicated in blue. I've still labelled it as T, and the mark comes from having a line that is steeper than the original, that is straight, and that is above. So theoretically, as long as you have a line that is somewhere along here, it doesn't really matter where it is. Mine's just indicated at a random point as long as it is going above the red one and again through 0, 0. Last few questions on the back. Experiments 1 to 6 were repeated using the correct volumes of A and B but no water added, and the rate was found to increase. Now if we're not adding water, we have got no longer a constant volume, a constant total volume. So what we'll find is that effectively we have got greater concentrations. If we've got greater concentrations, we've got an increased number of collisions, and that's what leads to our rate being faster. A graph of 1 over t against the volume of B would no longer give a straight line because the total volume is no longer constant. If we look at the numbers and we're saying that we're adding together A and B but no water, A and B but no water, so we're taking out this, then we can see we've got 10 and 55, 10 and 45, 10 and 35. So our total volumes are no longer constant. Suggest why 1 over t is only approximately proportional to the initial rate. Now, we discussed this in class. We've said that the rate is assumed to be constant from the point in the reaction that you add the two chemicals together to the point in the reaction that is being timed. Now, this isn't actually true, but it's an assumption that we use to enable us to process the data. It is true enough for us to process the data and extract the information that we need. It's only when we get to degree level and PhD level that this assumption will start to pose problems for calculations. Last couple of questions. In experiment 6, we're repeating it and we're using the volumes in the table, but the amount of HSO3- in the solution was doubled. The time for the pink colour to appear more than doubled. Explain why the time taken was more than twice as long. This is simply because the rate slows as the reaction proceeds. That's true for most reactions. Because some of the reactants are being used up, the concentrations are therefore decreasing, and as the concentration decreases, we will have fewer collisions, and therefore the rate of reaction will slow. So it's a traditional curve going down as the rate will slow down. Final question, again, given quite a lot of information. Give one reason why this method would not allow the student to determine the order of reaction with respect to sulfate ions. Now it's telling us that we could do this by keeping the volume of solution B constant and using different volumes of solution A, water still being added to keep the total volume constant for the mixture. But we have to remember that solution A contains not just the SO3 2- that we're looking at, but also HSO3- and your phenolphthalein indicator. So in this particular example, if we are going to alter the amount of solution A, we need to recognise that we're altering therefore the concentrations of two things, not just the SO3 2-, but we're also altering the concentration of the HSO3-. And if we have one element that is not constant, we can use that to find the order of a reaction. But if we have two elements that were not constant, then that means that we're unable to determine whether the changes are due to one particular aspect being changed or whether they're due to a separate aspect that's being changed. And that represents the end of evaluative task 1.